At the Danish construction site near Rodbyhaven, excavation and foundation work for the Femernbelt Tunnel is progressing. Similarly, the German site at Puttgarden is advancing with tunnel entrance preparations and segment assembly for this vital transport connection. The Almonty Viaduct spans 996 meters with a record-breaking 384 meters concrete arch, the longest railway arch worldwide. Its 14 meters wide, 3.1 meters deep box girder deck is supported by 23 spans and 22 piers, some reaching 65 meters high. Built using self-propelled formwork and segmental casting, it includes 60,000 cubic meters of high-performance concrete and 18 temporary tension cables. Quay wall construction at Amalia Haven involves deep foundation works using 31-meter-long steel pipe piles and combi wall techniques, integrating sustainable and digital innovations. The Port of Callao, Peru's main Pacific gateway, underwent major modernization after APM Terminals secured a 30-year concession in 2011. The FCC consortium rebuilt berths 5 and 11, expanded the container yard to 157,000 square meters, and added advanced infrastructure, including 5-story admin buildings and 600 reefer plugs. 4 Super Post Panamax STS cranes and 12 RTG yard cranes were installed, raising capacity from 900,000 to 1.2 million TEUs. Innovative cofferdams allowed underwater construction on steel piles. A new OCR-based truck access system and underground conveyor tunnels enhanced efficiency. Over 7.2 million man-hours were completed with top-tier safety standards, transforming Callao into a world-class port. The 221st and final caisson for Tuas Terminal Phase 1 has been successfully installed. This marks a major milestone in Singapore's port expansion. The terminal will unify port operations by 2040 and handle up to 65 million TEUs annually. The third Bosphorus Bridge features 322-meter pylons constructed using advanced slip-forming technology. With 1.5-meter-thick triangular cross-section walls, the pylons were built rapidly and precisely using continuous concrete casting. Opened in 2016, this iconic structure connects Europe and Asia near the Black Sea and stands as the tallest suspension bridge and second tallest bridge globally. The construction of APM Terminal's Medport Tangier by Williman Group involved complex, high-precision civil and infrastructure works across a 60-hectare site. Key components included the installation of 12 ship-to-shore STS cranes, automated rail-mounted gantries, ARMGs, and shuttle carriers. Foundation works incorporated over 414 reinforced concrete piles, 1,350 millimeters, L equals 26 meters, supporting load-bearing beams for STS rail systems. A 1,000 kilometers underground utility network, comprising electrical conduits, fiber optics, water, and sewer lines, was integrated into the structural layout. For stacking crane alignment, Williman developed a laser-guided concrete grinding system ensuring MLAC level tolerance. Over 20 million interlocking pavement blocks were installed, including 730,000 embedded guidance magnets for automated vehicle navigation. Reefer zones were equipped with 51 powered racks and 3 substations. Surface finishing included cement-treated base layers and container-grade asphalt. Structural works extended to 2-level workshop facilities for equipment maintenance. Power infrastructure included 1 intake and 3 distribution substations. Fire suppression was secured via 5 pump stations and 90 hydrants. Throughout the project, quality control included on-site laboratory verification of concrete mixes. Final commissioning was achieved through 40-phased milestones. The facility is designed for an annual handling capacity of 5 million TEUs, with full integration of automated and remotely monitored terminal operations via a dual fiber optic network. The construction of the £5 million rock revetment flood risk management scheme at East Toke Point, Hailing Island, was completed in 2013 to protect residential properties from coastal flooding. Led by the Eastern Solent Coastal Partnership in collaboration with Raymond Brown Construction Limited and the Environment Agency, the project focused on the installation of a robust rock armor revetment system. This involved placing large interlocking rocks along the shoreline to absorb and deflect wave energy, preventing erosion and overtopping during storm surges. The scheme was constructed along a vulnerable stretch of coastline, with views captured from both the eastern and western ends of the site. Key phases of the work included excavation and profiling of the shoreline, installation of geotextile underlayers for stability, and the careful placement of thousands of tons of imported rock. The revetment was designed to withstand extreme tidal conditions, providing long-term resilience for the community. Environmental and logistical considerations played a significant role in the construction process, with work planned around tidal windows and strict adherence to ecological protection measures. The East Toke Point scheme now serves as a model for sustainable coastal defense in the region. The Tuas Megaport caisson production process supports Singapore's land reclamation efforts. Each 15,000-ton caisson is cast from concrete in a slip-form structure. The process begins with casting the base slab, using vibrating rods to ensure even distribution. Then, towers are built layer by layer with reduced-weight internal frameworks. Hydraulic jacks raise the formwork as each layer is poured. Once complete, caissons are transferred via steel tracks to floating docks and towed out to sea. There, they're aligned, submerged, and joined to others, forming seawalls that define Singapore's expanding coastline. The caisson prefabrication and transfer process at Port Nador West Med, Morocco, follows a detailed sequence ensuring precision and efficiency. The operation begins with the placement of steel reinforcement for the caisson's base slab, radier, followed by the concrete pouring to form the base. Once cured, the base is transferred from Stage 1 to Stage 2, where the slipform system is installed. The slipform structure is lowered and prepared for the vertical casting of the caisson walls. Reinforcement and concreting of the vertical walls are carried out continuously, 24 hours a day for 5 to 6 days, depending on the setting time of the concrete. After completion of the upper structure, a transport barge docks to receive the caisson. The caisson is carefully positioned and installed at its final location. Once in place, additional structural components are mounted onto the caisson. The barge, specially designed to submerge partially while carrying the caisson, is then towed to the deployment site. The final stage involves the controlled submersion and precise placement of the caisson into the sea. This meticulous process ensures that each caisson meets high structural and durability standards, supporting the long-term development of the Nador West Med port infrastructure. Offloading a ship-to-shore crane manufactured by Mitsui E&S involves complex heavy-lift operations. Upon arrival at the port via a specialized transport vessel, The crane is carefully positioned using hydraulic skid systems and ballast adjustments. The crane is then rolled onto the quay using self-propelled modular transporters. Once ashore, final assembly and commissioning take place, including the installation of electrical systems, rails alignment, and load testing before operational deployment. Concrete gravel boards are made by mixing cement, sand, gravel, and water into a durable blend. The mixture is poured into steel molds with reinforcing steel bars for strength. After vibration to eliminate air pockets, the boards are left to cure and harden. Once demolded, they are stacked for full curing before use in fencing systems. The construction of the Nasibi Bridge, Turkey's first domestically designed and executed cable-stayed bridge, was a complex infrastructure project that began in 2012 and was completed in May 2015. Located over the Ataturk Dam Reservoir, the bridge was built to restore direct transportation between Adıyaman, Şanlıurfa, and Diyarbakır after the region was divided by the dam's formation. The project commenced with extensive geological surveys, topographic mapping, and controlled blasting operations to prepare the foundation. Approximately 150,000 cubic meters of rock were excavated to construct the bases for the two main pylons, each formed in an inverted Y shape and standing 96 meters tall. These foundations were reinforced with high-strength C50/60 concrete and 4,200 tons of rebar, ensuring structural resilience against a 2,475-year return period earthquake scenario. The pylons were constructed on both sides of the reservoir, Kata and Siverek, using entirely local resources, construction materials, and engineering expertise. Meanwhile, 6,500 tons of structural steel were fabricated at a factory in Osmaniye, pre-assembled into 250-ton deck segments measuring 440 square meters each, and then transported to the construction site using custom trailers. On location, the segments were assembled with high-precision welding, totaling 712 kilometers of welded seams. For installation, heavy lifting systems specifically engineered by Gulsan Holding were used to place the massive segments, some of which had to be floated across the dam, using specially adapted barges and positioned directly from the water, a first in Turkish bridge construction. Each segment was connected by two main cables, composed of 150 square millimeters steel strands made from twisted 7 millimeters wires. A total of 80 stay cables, ranging from 67 to 217 meters in length, were tensioned and anchored between the pylons and approach viaducts. Due to daily temperature fluctuations reaching up to 10 degrees Celsius, each segment's position had to be recalculated hourly to accommodate for thermal expansion and contraction. Up to 10 centimeters of longitudinal movement was recorded in some cases. Seismic, thermal, wind, and humidity sensors were embedded into the structure for long-term remote monitoring of operational safety. A notable technical challenge occurred during a severe drought in 2014 when water levels dropped significantly, causing a heavy transport barge to become grounded. Engineers responded by extending a temporary steel girder by 17 meters and converting it into a simply supported beam using stay cables, thus restoring lifting capabilities without delay. Without this solution, the project would have been delayed by nearly a year. After 3 years of continuous work, the final 6-meter-long key segment was lifted into place in early 2015, successfully connecting the bridge span. Despite the project's scale and complexity, it was completed without any fatal accidents and with minimal environmental impact, thanks to integrated quality, safety, and environmental management systems. The Nasibi Bridge was officially opened in May 2015, symbolizing not only an engineering triumph, but also the realization of a national dream, a major infrastructure project built entirely by Turkish engineers, workers, and materials, setting a benchmark for future bridge construction projects in the country. Anatolia has long been known for its trade routes, caravanserais, and stone bridges. Throughout history, thousands of bridges have been built across rivers that seemed impossible to cross. Some lost over time, others still standing strong. One such example is the Uzun Köprü, constructed in 1443 by architect Muslihidin under Sultan Murad II. At 2,392 meters, it remains the longest stone bridge in the world. In the same region, a modern engineering marvel is rising, the 1915 Çanakkale Bridge. Spanning the Dardanelles Strait, this suspension bridge will have the longest mid-span in the world, measuring 2,023 meters. The project involves 3 major construction sites, each dedicated to different components of the structure. For the foundation, 357 steel piles, ranging from 21 to 46 meters in length, were driven deep into the seabed. Each caisson foundation weighs 80,000 tons and is supported by specially engineered steel shafts. Interestingly, the ground reinforcement techniques echo those used centuries ago. Just as Ottoman engineers strengthened the soil with stone and timber piles, today's teams employ modern materials and advanced geotechnical methods to stabilize the seabed. Moreover, environmental sensitivity is central to the project. Marine life protection teams, including dolphin observers and underwater acoustic monitoring systems, have been deployed to minimize impact on the ecosystem. Once completed, the bridge will not only hold a world record for its span, but also serve as a vital part of the Malkara-Bandirma motorway, creating a new transportation corridor between Asia and Europe. The 1915 Çanakkale Bridge stands as a symbol of progress rooted in history, blending ancient engineering wisdom with cutting-edge technology and environmental awareness to leave a lasting legacy for future generations. It connects continents, cultures, and centuries, representing not only structural brilliance, but also the human spirit's enduring ambition to connect and overcome challenges through innovation and unity. The construction of the new Ocean Railway Bridge was executed through a carefully coordinated series of engineering operations within a strict 7-day rail closure window. The process began with site preparation, including rail isolation, traffic control, and environmental safeguards. The existing embankment and undersized culvert bridge were then removed using excavators and sheet piling equipment. Next, deep foundations were constructed by driving reinforced concrete piles into the ground, followed by casting pile caps and abutments on site. Once the substructure was complete, the new bridge deck, either precast or modular, was lifted into place using cranes with precise alignment to meet railway loading and canal clearance standards. After the deck was installed, the site was backfilled using granular material and geotextile layers to ensure stability, and the railway track was reinstated with new ballast, sleepers, and rails. Final works included drainage connections, waterproofing, and rigorous safety inspections. The project was completed on time, enabling both rail traffic to resume and boat navigation under the restored canal section. The production of concrete gravel boards begins with the preparation of the mold, which defines the board's dimensions and surface texture. Steel reinforcement bars are cut and placed inside the mold to provide structural integrity. A concrete mix, typically composed of cement, sand, gravel, and water, is then poured into the mold. Vibration is applied to remove air pockets and ensure even distribution. After pouring, the concrete is leveled and left to cure, usually for 24 to 48 hours. Once hardened, the board is demolded, inspected for quality, and prepared for shipping. These durable boards are used at the base of fence panels to prevent moisture damage and soil contact. The water pipeline installation process by Precision Pipeline begins with route surveying, alignment marking, and site preparation. Excavators then dig trenches according to design specifications. Steel pipes are lowered into place using specialized cranes and joined by automated or manual welding. Weld joints are inspected using ultrasonic testing and coated for corrosion protection. Finally, trenches are backfilled, surface restoration is completed, and the entire line undergoes pressure testing for quality assurance. Some years ago, Bitubau emphasized innovation and sustainability in road renovation. Their modern and eco-friendly production facilities enabled the efficient manufacture of high-quality materials. Specializing in thin-layer coatings, it offered durable surface treatments that significantly extended road lifespan while minimizing material use. Their expertise in applying DDK systems ensured optimal adhesion and resistance to wear. Additionally, focused on joint rehabilitation, using advanced sealing techniques to prevent water infiltration and structural damage. This comprehensive approach, combining high-performance surface treatments with precise joint restoration, demonstrated Bitubau's commitment to quality, longevity, and environmental responsibility in infrastructure maintenance. Their methods provided sustainable, cost-effective solutions for long-term road performance. Lohn and Sorgung deployed a large surface cleaning machine for deep cleaning of weathered paved surfaces. Wild weed brushes were used to remove overgrowth and clean the edge of the pavement. To minimize emissions, the area was pre-wetted. The system used 95 degrees Celsius hot water at 220 bars in rotating jets, with added surfactants, achieving a throughput of 20,000 cubic meters per hour with rear-mounted suction. The oil surfactant water emulsion was completely extracted. A handheld device delivering 300 bars water pressure was also used for targeted cleaning and dirty water removal. Additionally, high-pressure cleaning of a paint shop hull was performed, with continuous suction to maintain cleanliness. Heavy traffic and poor reinforcement often cause severely damaged road shoulders. requiring frequent regrading and filling with soil or gravel, leading to high maintenance costs. Bosch offers an efficient solution with grass paver installation. These pavers reduce wear, improve drainage, and increase traction in wet or icy conditions. Their open structure helps prevent water accumulation, and their vibration effect alerts inattentive drivers. With a single clamp, 5, 10, or 20 pavers can be picked up and laid individually, in pairs, or in parallel rows. Key steps include trench shaping, backfilling with gravel, smoothing and compacting with profile blades, laying pavers, and optionally filling and compacting with preferred materials. The container production process at Kluisberg begins with steel preparation and the manufacturing of the container frame. This is followed by priming and detailed production planning. Electrical and utility lines are then installed, along with ceiling and floor structures. Windows are fitted, and in-house manufactured elements are used for wall installation. The roof is assembled next, followed by painting. Electrical and sanitary systems are installed before a comprehensive quality check ensures all standards are met. Finally, transport and logistics operations ensure timely delivery. Kluisberg's process guarantees efficient, precise, and high-quality modular construction. Many years ago, the RCCU project at Esser-Stanlow involved a series of highly specialized heavy lifts, beginning with the installation of a custom-built steel transport frame to support the old regenerator head. This frame was moved into position using self-propelled modular trailers, SPMTs. The core of the lifting system was a skid mechanism, built from two 40-meter-long, 52-ton steel beams previously used in the recovery of the Russian submarine K-141 Kursk from the Barents Sea. All major lifts were executed using a platform twin-ring containerized crane, whose main boom, once erected, reached 103 meters in height, towering over the FCCU unit. The original regenerator vessel was partially dismantled by milling through its 32 millimeters thick steel shell to release the top section housing the cyclones. A new regenerator head, weighing 481 tons, was then positioned on the skid bridge and lifted into place over the course of 2 hours. The lift demanded exceptional precision. Across the 14-meter diameter interface, a tolerance of plus or minus 10 millimeters was required, but fabrication achieved an extraordinary 1 millimeter accuracy. The project also included replacing the overhead line, with the new sections carefully transported across the site and lifted into position above the cat cracker. This high-stakes operation was completed safely and successfully. The flange production process begins with the careful selection of raw materials, ensuring the steel meets strict mechanical and chemical specifications. Once selected, the steel is cut into blocks or blanks of the required size based on the desired flange dimensions. These blanks are then placed into a high-temperature furnace for uniform heating. After reaching forging temperature, the heated steel is shaped into a flat, round form using mechanical presses or ring rolling. It is then forged into the final flange shape through precise hammering and pressing techniques. Once forged, the flange is gradually cooled under controlled conditions to prevent internal stress and deformation. The cooled flange is then drilled to create bolt holes and shaped further depending on the required specifications, e.g., face type, bore size. Finally, each flange is cleaned, surface treated, e.g., anti-corrosion coating, marked with technical information, and carefully packaged for shipment. This structured process ensures each flange meets required standards in terms of strength, durability, and dimensional accuracy. Gotei Hydropower specializes in manufacturing of hydropower turbine components runners using monoblock forging and 100% CNC precision machining. In the hot rolling process, several key components work in sequence to transform heated steel slabs into coiled products. First, the mesa roller table transports the red-hot slabs from the reheating furnace to the laminador roughing mill, where initial thickness reduction occurs. After roughing, the material is passed to the flying shear, which trims the head and tail of the strip while in motion. The slab then enters the trem acabador finishing mill train, consisting of multiple stands that progressively reduce the strip to its final thickness. Once rolled, the strip passes through the secondary scale breaker outlet, where high-pressure water jets remove residual scale. Finally, the strip is stabilized and secured by the strapping machine, which applies steel bands to hold the coil firmly before storage or transport. UMS manufactures light steel frame volumetric modules using lean production and CNC precision. Modules are pre-fitted with services, tested, insulated, and sealed for transport. Designed for student, military, and hotel use, they allow rapid on-site installation without extra structural support, reducing time, waste, and foundation loads. The plywood manufacturing process begins with a selection of high-quality natural wood. The wood is cut into thin layers called veneers, which are then dried to reduce moisture content. Next, glue is applied to the surface of the veneer layers, which helps the layers of wood stick together when pressed. The layers of wood are stacked and fed into a press under high temperature and pressure, forming a complete plywood panel. The panels are then cut, sanded, and finished for quality control before being packaged and shipped. After the plywood has been completed and quality checked, the sheets are carefully packed and transported to the construction site to form the roof frame of the wooden house. The roof frame installation will be carried out by a team of technicians, utilizing specialized equipment to ensure precision and durability for the roof structure. At the Collins Lakeview Sawmill, the timber processing workflow begins with log scaling, where logs are measured and graded to determine their commercial value. The next step is debarking, which removes the bark to protect downstream equipment and ensure cleaner cuts. The debarked logs are processed through the single-pass saw and head rig, where they are broken down into rough cant blocks. These cants move on to the resaw, where they are further cut into thinner boards. For naturally curved logs, the curved gang saw uses adaptive cutting paths to maximize yield by following the wood's curvature. After cutting, boards are automatically stacked with spacers using the sticker stacker, facilitating airflow prior to drying. The stacked lumber enters dry kilns, where moisture content is reduced to improve dimensional stability and prevent warping. In the finishing phase, boards pass through a planer to achieve smooth, uniform thickness. During grading, lumber is visually or mechanically assessed and classified by quality. Boards are then trimmed to standard lengths and grade stamped with official grading marks. At the end of the line, boards are bundled using a bander, then paper wrapped and tagged, for protection and identification. Finally, the products are prepared for shipping to customers or distribution centers. The entire process is designed for efficiency, quality, and consistency, delivering high-grade, dimensionally stable lumber to meet a variety of market needs. Launched by Rengli AG in March, the Vision R4 concept focuses on reducing housing to its essential components while integrating cutting-edge, energy-efficient technology. This project embodies the highest level of prefabrication to ensure both quality and cost control. The Vision R4, the first of its kind, is made up of 4 room modules that are carefully pre-assembled at the production facility. This advanced construction process ensures the modules are ready for rapid deployment. Within just a few days of assembly, the modules are transported to the building site. The structure is erected in a remarkable 4-hour time frame at the Stillhouse Garden in Rothrist, Switzerland. Following the rapid installation, the house is fully completed and ready for occupancy within a single day. The Vision R4 house is not only a showcase of modern prefabricated building techniques, but also a symbol of efficiency and sustainability. Visitors are invited to tour the completed structure, offering a real-life example of the future of residential construction. The Pinosa EPC 400 is recognized as the world's fastest firewood processor, engineered for high volume and efficient firewood production. Designed for continuous automatic operation, it handles logs up to 480 millimeters in diameter and 6 meters in length. The EPC 400 features an integrated log infeed system, circular saw cutting, and powerful splitting capabilities. The machine includes an automated control panel for single operator use and precise production management. Its robust steel frame ensures durability under heavy workloads, while advanced hydraulic systems drive efficient cutting and splitting. With its compact design and mobility options, the EPC 400 is ideal for both industrial-scale firewood suppliers and remote logging operations. The Petzolato TLA 150 firewood processor is designed for large-scale firewood production with a single operator, offering efficient, high-capacity processing. This machine features a maximum log diameter of 600 millimeters, a splitting force of 70 by 2 tons, and is powered by a 55 to 75 kilowatts electric motor. The cutting length ranges from 20 to 65 centimeters, making it versatile for various firewood sizes. It integrates a wood splitter with a circular saw, streamlining both the cutting and splitting stages. This combination allows for faster and more efficient firewood production. The TLA 150 is particularly suited for high-output operations, making it ideal for businesses needing to process large volumes of firewood. It is widely used in firewood production lines due to its durability, speed, and precision. The processor is designed to minimize operator effort while ensuring consistent and reliable performance, making it a top choice for professional logging and firewood production. Oregon Canadian Forest Products specializes in high-grade softwoods, notably Douglas fir, hemlock, and western red cedar. Logs are sourced from the Pacific Northwest and processed using advanced equipment like McDonald resaws, Sherman edgers, and Stetson Ross planers. 5 natural gas-fired kilns, controlled by an SCS monitoring system, ensure precise drying. Post-drying, lumber is graded, sorted, and milled into premium products for global markets, all under sustainable forestry certifications like PEFC and SFC. The Petzolato Professional 2.0 is a high-performance firewood processor designed for operation by a single user. Engineered for efficiency and safety, it handles logs up to 520 millimeters in diameter and 6 meters in length. The machine integrates cutting, splitting, and conveyor systems into a compact unit, streamlining the firewood production process. Its user-friendly control panel ensures simple operation, while robust construction and advanced hydraulics guarantee reliability and productivity. Ideal for professional firewood producers seeking high output with reduced labor requirements. The 2020 sugar beet piling process involves both side dumps and end dumps to efficiently unload harvested beets at receiving stations. Trucks arrive loaded with beets and are directed to designated dumping areas. Side dump trucks tilt their beds laterally, while end dumps raise the bed from the rear to discharge the load. The beets are funneled onto conveyors that transport them into massive piles for storage. Operators carefully manage flow to avoid damage to the beets and ensure even distribution. Bulldozers and leveling machines are used to shape and compact the piles. This method allows rapid handling of large quantities during harvest season, minimizing wait times for drivers and preserving beet quality for processing at sugar factories. The Petzolato TLA13 firewood processor is a high-performance, industrial-grade machine designed for processing large logs and irregular wood bundles. Capable of handling logs up to 510 millimeters in diameter, it is built to work efficiently with both large, mixed, and irregular wood materials, making it ideal for high-output operations. This firewood processor integrates a circular saw with a wood splitter, providing a seamless solution for both cutting and splitting wood in one operation. It is particularly suited for processing firewood for commercial use, where high production rates are required. The TLA-13's robust design ensures reliability and consistency, while the integrated system reduces the need for multiple machines, optimizing space and workflow. The Pezzolato TLA-13 is equipped with an advanced splitting force system, allowing it to handle difficult-to-process materials with ease. The machine's versatility enables it to efficiently process different wood types, including large, irregular logs as well as mixed bundles. Additionally, the TLA-13 offers excellent precision in cutting lengths, ensuring consistent quality in the finished firewood. With its heavy-duty capabilities, the Pezzolato TLA-13 is ideal for firewood production businesses that require high productivity, durability, and efficiency. This processor significantly enhances processing speed, making it a valuable investment for large-scale firewood operations and improving overall production capacity. Johann Pabst Holz Industry is a technically advanced wood processing facility located in Austria's forest-rich Murtal region. Raw logs are sourced locally and undergo precise sorting, debarking, and cutting using modern CNC-controlled saw lines. Automated systems ensure optimal yield and minimal waste. Kiln drying processes are carefully controlled to meet exact moisture specifications. Finger jointing and lamination techniques are used for structural timber production. The PPC 1300 is a fully automatic firewood processing center designed for high efficiency and productivity. Logs are fed into the machine, where they are automatically measured, cut to preset lengths, and split with hydraulic force into uniform firewood pieces. The system features conveyor-fed input, an integrated log saw, multi-blade splitting system, and automated outfeed for continuous operation. The PPC 1300 is equipped with safety enclosures, programmable settings, and remote control for minimal manual intervention. Ideal for large-scale firewood production, the unit ensures consistent output, reduced labor, and optimized log utilization, making it a highly efficient solution for commercial wood processing operations. The PPC 1500 is a high-capacity semi-automatic or fully automatic firewood processor designed for single-operator use. It is built to handle a wide range of log sizes and is suitable for both industrial and commercial firewood production. The machine accommodates input material lengths of 3,500 mm to 8,000 mm and processes them into segments ranging from 110 mm to 550 mm in length. It can work with logs up to 600 mm in diameter. Equipped with a powerful splitting mechanism offering 25, 30, or 35 tons of force, the PPC 1500 ensures efficient processing of hardwood and irregular timber. The machine is available with various drive options, including an electric motor, diesel engine, or PTO drive, providing flexibility for different operational setups. Designed for high productivity and minimal operator effort, the PPC-1500 offers precise cutting, robust splitting, and reliable performance in demanding forestry environments. The Penosa CPE-1200 is a compact, self-loading firewood machining center designed for automatic operation and controlled by a single operator. Engineered for processing short logs and mixed mountain wood, the CPE-1200 is also capable of handling branchwood, sawmill offcuts, and carpentry waste efficiently. Its robust construction and design allow it to work with raw material up to 480 millimeters in diameter and lengths up to 10 meters, making it suitable for a wide range of forestry and wood recovery applications. The machine features an integrated self-loading system, which significantly reduces manual handling. Once loaded, logs are advanced through a mechanized infeed where they are cross-cut to preset lengths using a powerful circular saw blade. This is followed by splitting operations using a high-force hydraulic wedge system, which ensures precise and consistent firewood output. Control is centralized via an operator panel, allowing one person to oversee the entire processing sequence, from loading to outfeed. The machine is optimized for fuel wood production with minimal labor, making it ideal for both small-scale and commercial firewood operations. Its compact layout, automation, and adaptability to various wood types, especially irregular and reclaimed pieces, position the CPE-1200 as a highly efficient and versatile solution for firewood processing. Mellett's log and lumber conveyor systems, as implemented at Wagner Millwork in Owego, NY, are engineered to support high-throughput, precision-oriented sawmill operations. The process begins with the delivery of raw logs to the infeed deck, where they are steadily advanced to the debarker station. Here, mechanical arms and rollers strip away the bark to prepare the logs for accurate downstream processing. Once debarked, logs are conveyed to a primary head rig, where they are sawn into square cants. This square form facilitates consistent handling and optimizes subsequent cutting operations. The cants are then routed via robust chain-driven conveyors to secondary breakdown equipment, such as band resaws or gang saws, which process them into lumber boards of varying thicknesses according to market demand. Mellett's systems are modular and highly adaptable, allowing smooth transitions between stages while minimizing manual handling. Throughout the line, high-torque motors and custom-fabricated steel frames ensure durability and precise control under heavy load conditions. Integrated waste conveyors continuously collect sawdust, bark, wood chips, and offcuts, transporting them to dedicated storage or biomass processing units. This ensures clean work zones and efficient material recovery. The system's design accommodates both dimensional lumber and specialty cuts, maximizing yield from each log. Mellett's focus on synchronized system integration allows Wagner Millwork to achieve consistent high-speed operation with minimal downtime. Additionally, sensor-based control systems and variable speed drives allow dynamic adjustment of feed rates based on log characteristics and production goals. This level of automation not only enhances safety but also ensures optimal material flow. By incorporating advanced automation and control technologies, their systems enhance the precision of lumber sorting, tracking, and processing. This integration improves overall efficiency, reduces labor costs, and ensures consistent product quality, making Millet a key player in modernizing sawmills for the future.